Before we're going to look at the basic layout of modern microscopes, let's look at one of the first microscopes used in the world. Or maybe better, because microscopes have been around for quite some time, one of the first microscopes used by someone who documented his results, Antony van Leeuwenhoek. So Antony van Leeuwenhoek was a Delft textile trader in the 17th century who used to polish his lenses and achieved remarkable results with his polishing. The lenses he made could achieve magnification factors over 100 times, which, as we may note, is comparable to what we can achieve with current-day objective lenses in a microscope. So here we see an example of such a microscope built by van Leeuwenhoek. So you can see a metal plate in which, if you look carefully, there's a small hole with a tiny lens placed inside. Before this lens you see a small pin, and on this pin the sample was mounted. Now below the pin you see two screws. One screw is used to position the sample in the center of the field of view of the lens. The other screw is used to move the pin with the sample in and out of focus. Now this very simple microscope works with a single lens. And the magnifying properties of a single lens are known by the famous lens maker's formula. We see the ray diagram of a single lens system depicted here. So on my side of the lens you see the object, and on the other side of the lens, on the far side, you see the image. So we can find the position of the object by ray tracing rays from a point in the object plane. In this case we take a point in the sample, which goes paraxial to the lens, which then is refracted by the lens to go through the focal point, and we also take a ray going through the center of the lens, which stays unrefracted. The crossing point of these rays then determines the position of the same point on the object on the image plane. Now the magnification by such a lens is given by the ratio between the image plane, the image distance and the object distance. And the relation between these two is governed by the focal distance of the lens, f. The smaller the focal distance, the higher the magnification, or in other words, the more the lens refracts the rays, so the larger the angle of rays, the opening angle of rays in the object plane, in the image plane, the stronger the lens works. Now we can use such a single lens system and these formulas if we position a recording device, a camera or a piece of paper on the image side of the lens. However, in practice we are looking at a sample with our eyes, just like in the microscope of van Leeuwenhoek. So in this case it works slightly differently, because our lens also has focusing properties. So in this situation of van Leeuwenhoek's microscope, we have the lens system, we look at it through the backside in the picture that you see, depicted in the ray diagram here, and then on the other side the sample is placed. So we can now ray trace the rays in the same way as we did before, only now we have to realize that we put the sample in the focal plane of the lens. So now if we look with our eyes through the lens at the object seems to appear from further away behind the lens, giving us then again a magnification. And here the same thing holds: the shorter the focal distance, the stronger the lens. We should also notice that the stronger the lens, the shorter the focal distance, the smaller the field of view of this lens. So this is one of the realizations that we also have to make in van Leeuwenhoek's lens. The magnification was very high, but the field of view was very small. One of the limitations that is solved in present-day microscopes. Now this is just a single lens system. So if we look at a modern microscope, we see that it's much more complicated than just a single lens. So here you see an image of a modern-day microscope. So again, we can distinguish a single lens, which we call the objective lens, with a magnification of up to 100 times. But we also see additional lenses. Most striking is here we see the eyepiece lens, so an additional lens that allows us to look at the sample, which gives an additional magnification of about a factor of 10. And we see a mount for the camera if, instead of looking at the sample by eye, we wish to record the images from the sample. By the way, also something that van Leeuwenhoek was not capable of. He had to draw the images that he saw himself. So now we basically have a two-lens system. And a two-lens system is what we call a compound microscope or a multi-lens system. And a compound microscope works a bit differently than what we had before. So here on the object side, we see the objective lens, which collects the light originating from the object. It can be projected as in the same way via the lens maker's formula and the ray tracing, and it produces an intermediate image. This intermediate image is then observed if we look by eye through the eyepiece, and that gives us the additional magnification in the same way as it did with the single lens system we saw before. And note that the total magnification is now given by the combination of the magnification of the objective lens, typically a factor of 5 to 100 times, multiplied by the magnification of the eyepiece, typically a factor of 1 to 10. Now, in essence, this is a two-lens system, but in practice the modern microscope contains much more elements and much more lenses. You see that depicted here schematically. Now, in all these complicated ray traces and all these elements, we can distinguish several key factors. First, we should note that we have a dedicated lighting system, in this case a lamp unit. The lamp unit, you see it on two places, one above the sample, one below. The lamp unit is a part of the total illumination system. So there's two illumination systems, one for if the light comes from below the sample, one if it comes from above, and you see them in the dashed red boxes. So the lenses in these lighting systems, in the illumination systems, are meant to take the light from the source and project it homogeneously onto the sample. Of course, the other essential part is the sample holder, where we have the object that we inspect, or the specimen. Now, if the light originates from the sample or generates a signal in the sample, that light, signal light, is collected by the objective lens and then goes through a set of lenses in the blue dashed box here, which is the image forming part of the microscope. Again, this can be composed of several different additional lenses or other elements, and it typically splits for a light microscope into a part that goes through the eyepiece or a part that goes through the compound microscope. Now, why are there now so many additional lenses? In essence, we have seen that we only need two lenses, the objective lens and the eyepiece. Well, one reason is that in the illumination part, we need a lot of lenses to make the image of the source of the lamp unit homogeneous over the sample, at least over the imaging, the area we are imaging in the sample, so we don't want intensity variations that originate from the light source. The other thing is that in the image formation part, we correct for a lot of aberrations. One famous aberration that we have in light microscopy is chromatic aberrations. So chromatic aberrations refer to the refractive index of the lenses being stronger in the blue part of the visible spectrum compared to the red part of the spectrum. So this means that a focal point shifts, and that if one wavelength, one color is in focus, another wavelength or another color is not, leading to a blurring. So many of the objective lenses we use nowadays have multiple lenses that in total correct for these aberrations as much as possible. You see that depicted here. Another reason for all these lenses with all different kind of polishing is to make sure that we have a large field of view over which the illumination is in focus and homogeneous, contrary to what we saw in van Leeuwenhoek's microscope, which was only a single very, very sharply polished lens with very high curvature, which then only gave almost a spot-like image.